As we continue discussing probability, we will go into the theoretical and experimental probability of something occurring. So calculating the theoretical probability, the probability is the likelihood of an event occurring. Now, if all outcomes are equally likely, then the theoretical probability of event A will occur is, let's see, what are we talking about here? We're talking about, is something going to occur? Well, it's the number of favorable outcomes divided by the number of possible outcomes. So that's how we figure out the ratio of probability. And in doing so, we think about it, if I'm going to, an example here is the probability of rolling a 3 on a number cube. Well, there are 6 numbers on a number cube, so the probability of rolling a 3 would be 1 in 6. Also, if you think about the probability of flipping a coin and it landing on heads. Well, you have 2 choices. You've got heads or tails, so the probability of that is going to be about 1/2. So that would be, looking at the number line, the difference or the probability from 0 to 1, and if you think about it, 1 is 100% chance, or 0. And then, so the probability of rolling that 3 is about 1/6. The probability of flipping that coin and landing on heads or tails is 50%. So that's how we sort of think about the probability of the favorable outcomes over the possible outcomes. And just thinking about it, the closer that I am to 1, the more likely something is going to occur, versus the closer I am to 0, the less likely it is going to occur. So as we look, we took here example number 1, and Erin rolls a number cube. And what is the possibility that she rolls a number less than 5? Well, the sample space, so the number of possible outcomes, she could roll a 1, 2, 3, 4, 5, or 6 on a 6-sided number cube, right? And in doing so, the favorable outcomes, we're looking at the probability that she rolls less than a 5. Well, the values less than 5 are 1, 2, 3, 4. And therefore, we're looking at the favorable outcomes would be 4 over the possible outcomes of 6, which is 2/3 or approximately 67%. And since 67 is greater than 50%, it is in the more than likely to occur category, because it is approaching or greater than 50% or closer to 1 than 0. Now, in this case, we could look here and say that, hey, all my favorable outcomes are actually a subset of my sample space, and that's what they're talking about here, is A is a subset of my sample space. And then again, we just talked about it, that the event is more likely to occur. And why? Because it's greater than 50% chance. And that, in a nutshell, is talking about our theoretical probability. So in example number 2 here, it says a pencil box contains 5 red, 12 blue, 10 green, and 3 yellow markers. If a marker is chosen at random, what is the probability that it is not yellow? Okay, not yellow. We're going to talk a little bit more about complements in a minute, but not yellow. Well, a total of, favorables versus the totals. If I reach into that pencil box, how many markers do I have total? I have 5 plus 12 is 17, plus 10 is 27, and plus 3 is 30. So I have a total of 30 markers. And I could say that, well, I have 3 yellow markers, so 30 minus 3, I have 27 other possible markers in there that I could pull out. So if a marker is chosen at random, what is the probability that it is not yellow? Well, the probability is going to be about 9/10 or 90%. And that's the probability of it being not yellow. Conversely, if it was yellow, let's see, favorable, I have 3 markers that are yellow out of 30, which is going to be 1/10 or 10%. 10% chance that it would have been yellow, or 90% chance that it was not yellow. And if you'll notice, and we're going to talk about it here in a minute, that my chances and my not chances totaled up to be 1. And that's where we talk about that complement. All right, so looking here at example number 3, what is the probability of drawing a queen or heart from a standard deck of playing cards? Well, let's talk about the total. Let's talk about the favorable. And so the total might be the easiest to look at first. The total number of cards that we have in a standard deck of playing cards is going to be 52. Now, looking at that, let's think about the favorable outcomes. They want us to pull a queen and they want to pull a heart. What are the probability of that happening? Well, there are 13 hearts, 2 through ace, and that is going to be 13 hearts. And one of those is going to be a queen, and then I'm going to have 3 other queens. I'm going to have the queen of diamonds. I'm going to have the queen of clubs. And I'm going to have the queen of spades. Not some very good symbols there, but so we have 13 possible hearts plus 3 additional queens, so there's going to be 16 over 52 probability, which is going to simplify down to 4 over, no, it's not going to be 4 over 13. Let's see, it's going to be 8 over 26. And continuing on, it looks like it simplifies down to 4 over 13 probability, or approximately 31% chance. So there you go, 31% probability that we would pull one of those 16 cards out of a standard playing deck. Now, talking about the complements, that's what I was getting to just a moment ago. Sometimes we can determine something by looking at its complements, determine the probability by looking at it, the not probability, should I say. So the complement of event A, denoted by A raised to the C, consists of all outcomes that are not in the event. So some examples: if I had this event, drawing a blue marble out of a bag, hey, the complement to that would be not drawing that blue marble out of the bag. A lock with all even digits, well, the complement to that would be a lock code without all even digits. It could have some even digits in there, just not all of them being even. And then a dart landing in the bullseye on a dartboard, the complement would be the dart not landing in that bullseye. Because we're learning here to analyze these complements, that the probability of the event happening, right, plus the probability of its complement should total 1, or 100%. And if I were to look at that, the complement is going to be 1 minus the probability of the event happening. So those two things are the same, just sort of manipulated using, algebraic skills. So just understanding this. So let's see here, the probability, looking at example 4, the probability that it will rain tomorrow is 11/15. What is the probability that it will not rain? Well, the probability that it will not rain, the complement, is equal to 1 minus the event, which is going to be 11/15, or 4/15, that it will not rain tomorrow. Excuse me. And let's see here, looking at example number 5, a number from 1 to 30 is selected at random. What is the probability of not selecting a multiple of 4? Well, let's see, not selecting a multiple of 4. Well, let's think how many multiples of 4 are there between 1 and 30. I've got 4, 8, 12, 16, 20, 24, and 28. So it looks like I have 7 possibilities that could be a multiple of 4. So the probability of pulling that multiple of 4 is going to be 7 out of 30. Okay, and then we would have, say, well, if that was the probability, the complement of that event is going to be something along the lines of 1 minus 7 out of 30, or 23 out of 30 would be the probability of not selecting that multiple of 4. So there you go. We're just sort of looking at some of these theoretical probabilities, and of course possibly using the complement to determine that. Now, what we've talked about is what should happen, what we expect to happen theoretically. But sometimes we talk about experimental probability, and in experimental probability we're making determinations based on observation. Okay, so calculating that experimental probability is going to be how the probability of an event occurring based on the data that we're given. So we look at the probability again of the favorable outcomes divided by the number of trials. Versus, before we were talking about the number of possibilities of it happening. Here we're talking about trials, so we will look at it from a data-driven perspective based on the results of repeated trials. Charlie flips a coin 120 times. Out of 120 flips, heads appears 73 times. What is the experimental probability of flipping heads? Well, the favorable outcomes, it occurred 73 times, so the favorable outcomes was 73. The number of trials was the number of times that the coin was flipped, which was 120. So the probability of that event happening, of flipping heads, experimental probability, was 73 divided by 120. And when we simplify that, so continuing on again, looking at the number of options, number of favorable outcomes divided by the number of trials. Coming up here, we start talking about example number 6. It says, find the experimental probability that a student chosen at random has at least one, but no more than 2 pets. So looking at our chart over here, we have the number of pets here. Number of pets, 0, 1, 2, 3, 4, and then the number of students. Okay, number of pets, students, chosen at random. 1, but no more than 2 pets. So here we have 1, but no more than 2 pets. The number of students with 1 or 2 pets it's going to be right here, which is going to be 7 plus 8 is going to be 15. So the number of students, the number of favorable outcomes is 15. Now, the number of trials is simply, in this case, how many students do we have to choose from randomly? And that would be 15 plus 10, so that is going to be 25. So the probability of selecting a student at random that has at least 1, but no more than 2 pets is going to be the favorable outcome of 15 divided by the number of trials, which is 25. Also simplifies to 3 over 5. Or 60%. 60% probability of that occurring. So this is examining some experimental probability. Now, when we compare experimental probability and theoretic probability, it may not be the same. So here, looking at Jamie rolled a number cube 10 times. And her results were here, right? Here's the 10 rolls that occurred. 4, 5, 1, 3, 2, 2, 5, 6, 5, 2. Now, what was the experimental probability of rolling a 2? Okay, well, the number of trials was how many times did she roll? She rolled 10 times. So that is the number of trials, and then the number of favorable outcomes would be how many times did she roll that 2? 1, 2, 3. So she rolled a 2 3 times. So again, my favorable divided by the number of trials, which is going to be 3 over 10 or 30%. That would be my experimental probability. Now, if we look at theoretical probability of rolling that number cube and rolling it 2, we talked about it a minute ago. If I have a standard number cube, the probability of rolling any given number on there is going to be the favorability of rolling that number divided by the number of outcomes, which is 1/6. So the number of possible outcomes of rolling a 2 is 1. The number of favorable outcomes of rolling that 2 is 1. The possibility of outcomes is 6. So that is 1/6. Or, gosh, I hate doing math in public, approximately 16.7%. So in this case, my theoretical and my experimental probabilities do not match up. So just want you to see that they do not always match. And here we go, looking at another example of some information here. So it says, look at example number 7, a spinner is spun 50 times. The results of each spin are shown below. So here we go, we rolled red 5 times, orange 12, purple 7, yellow 16, and green 10. And then find the theoretical and experimental probability if the spinner is spun again. Okay, so the theoretical probability of rolling orange, not rolling, spinning that and getting an orange. Well, orange is on here 1 time, okay? So that is my favorable outcome is 1 over my possible outcomes, which would be 5, because there's 5 different colors on the wheel. That would be my theoretical outcome. Now my experimental outcome, when I rolled orange, our trial was 50 times they spun, and they came up orange 12 times, which simplifies to 6 over 25. So obviously here my 2 don't match up, very close, but not perfect. Now the options of rolling, or the probability here of rolling red or green. Okay, well again, that's 2 options out of 5 that you theoretically would possibly spin and land on red or green. But the options on the experimenting, well, red we had 5, green we had 15, so that would be 15 divided by the 50 total spins is going to leave me 3 out of 10, which again is a little bit off. This would be 4/10. We have 3/10, therefore, yeah, it's not the same. And then not purple. Okay, not purple. We have the chance of rolling or spinning and landing on not purple 1, 2, 3, 4 times. So the likelihood of not purple is going to be 4/5. And the experimental probability of not purple, well, we spun 50 times. We landed on purple 7. So therefore, 43 times we did not land on purple. So the probability of not landing on purple is going to be 43 out of 50. And there you have utilizing some of our experimental and theoretical probabilities and comparing them. So do a couple more examples here. So in example 8, students in a homeroom were asked if they had a part-time job and if they have their driver's license. The results are shown in the Venn diagram to the right, and if the student from the homeroom is chosen at random, find each probability, give each answer as a fraction in the simplest form. Good. Don't need a calculator with that. Let's see here. So the probability of having a part-time job. Well, I guess first of all, we can figure out how many students do we have total, because that's going to be our number of trials. So looking here, it looks like we have 7, 6, 8 students. So that's 21 plus 4 students over here that have neither a part-time job nor a driver's license. So we have a total of 25 students. So we know that most of our sampling should come out of that. That should be our total trials or total possibilities. So let's see here. So of a part-time job, we have 8 students, 6 students. So we have 14 students have a part-time job out of 25. The students that have no driver's license. Okay, well, it looks like I have students with a driver's license, 13, 7 plus 6 is 13, and then I have these 12 without. So with no driver's license, I have 12 out of 25 probability. Next, we have the part-time job and the driver's license. Well, that falls right here. That's my overlap. That's the intersection of part-time job and driver's license. So that is going to be 6 out of 25. Let's see here, D, part-time job and driver's license. Well, I'm sorry, part-time job or driver's license. And there we're going to add these up. So I'm going to have 8 plus 6 plus 7, and I'm going to hope that comes to, is that 21? 21 out of 25, because we do have these guys over here that have neither. And then last here we got the probability of a driver's license and no part-time job. So we have a driver's license, and these guys have a driver's license and part-time job. So these guys just have a driver's license. They're living free, got a vehicle, or got the ability or access, but no job to get them some gas money. So there you go. So that's how we can figure out some of that experimental probability. Looking at number 9, out of 60 students, 60. 15 are taking calculus, 27 are taking physics, 8 are taking both. Oh, good. Bless their heart. Although from everything I understand, physics and calculus are really two different animals. So it said here we have 8 students taking both. We have a total of 15 students taking calculus, so that means 7 students are taking calculus, and 15 total, and then 8 are taking both. And then we have these students over here taking physics, and there's 27 of them, 27 minus 8, so that means we have 19 over here that are taking physics just by itself. So total of 60 students, okay? And it says, let's see here, the probability that a student takes calculus or physics. Well, add them all up. Probability that they take those is going to be 15 plus 19, I'm going to go with 34. So the probability is going to be 34 students out of 60, or 17 out of 30 students, the probability. And then also looking at B here, the probability that takes calculus but not physics. Well, that would be this number right here. So the probability that they're taking calculus but not physics is going to be 7 out of the total, which is 60. And there you go, we have our probabilities. Just keep on rolling with these examples. Page rolls a number cube 64 times. Okay, so there's our total trials. Total. The number 4 comes up 14 times, okay? 14 times. And then the number 3 comes up 6 times. Rounded to the nearest whole percent, what is the experimental probability of rolling a 3 or a 4? Well, out of those, the favorable outcomes would have been rolling a 3 or 4 would be 6 plus 14, which is 20. So the favorable divided by the total is going to be 20 divided by 64. Remember, rolled that cube 64 times. That was the total number of trials. That is going to simplify to 10 over 32, or approximately 31%. There you go. So that is the experimental probability. And finally, our last example here, we're going to go with the standard dice are rolled. What is the probability that the sum of the 2 dots on the dice is at most 5? Okay, let's see here. When we're rolling a die, we can have, on one die, we can roll a 1 and a 1. We could roll a 1 and a 2. We could roll a 1 and a 3. We could roll a 1 and a 4. We could roll a 1 and a 5 and a 1 and a 6, right? These are the possible combinations. Then we could roll a 2 and a 1. We could roll a 2 and a 2. We could roll a 2 and a 3, and so on as we continue to roll our possible combinations. And I'm going to fill these in real quick. Okay, so these are the possible rolling combinations if I roll two dice. Let's see here. What is the probability that the sum of the two dots are at most 5? Well, let's see. If I do some highlighting real quick, this would be 2, so that's at most 5. So it looks like 4 and a 1 would be at most 5. A 3 and a 2 would be at most 5, a 2 and a 3 would be at most 5, and a 4 and a 1 would be at most 5. And all my other combinations out here, if I roll these are going to be greater than a sum of 5. So there we go. We know that now we're talking about what are the total rolls that I would have had. The total we were looking at was going to be 36. 36 possible combinations. And the favorable outcomes, of course, were going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 possible outcomes that met our condition of at most 5. That's going to simplify down to 5 over 18. And I'm not going to bother putting that into a fraction or a decimal because they didn't ask me to. But there you go. That's the figuring out the possible experimental probability of rolling the sum of less than 5. Now, and that is experimental and theoretical probability in a nutshell. We're going to do some practicing in class. We're going to come back and visit this over and over again over the course of this unit, but this should help us get started. And good luck.